Okay, so I think sometimes it is good to know historical perspective of how things came. So I'll tell you a little bit of history, and for that I'll give you another example of algorithm using websites. Okay, so I have already given you this algorithm, but that was an extremely magical algorithm. But that magical algorithm actually stems from this particular idea. So this is called directed K cycle, which I already directed long cycle. Okay. Input is d comma k, parameter is k, and the question is, does there exist a directed cycle of size at least k? Okay. So we saw why we cannot apply color coding or anything on this problem. Because I am not asking a directed cycle of length equal to k, I am saying at least k. So maybe the cycle which is greater than or equal to k, maybe it is Hamiltonian cycle for all that you care. The next long cycle greater than or equal to k has size maybe some function of n. So I cannot apply color coding because color coding uses number of colors which is proportional to the size of the object we are seeking for. Okay. And there was an algorithm with running time k power k times some poly in n by Gabos, Harold Gabos, SFU, what is this? Harold Gabos, Gabor, yes. GA, yeah, Harold Gabor. Okay, so he had k power. Exactly. So he had this algorithm for this problem, k power k in poly n, in soda 4 and transactions and algorithm. Okay. So at least my personal interest was to see if this problem has c power k algorithm or not. That was the only interest we had at that point of time. And I just had read Repset in lots of these kernel talks. So it looked like a great idea to apply one of these things here. And then we hit on this particular lemma which said, okay, and so this question is also interesting in undirected setting, right? So undirected setting also, but this undirected setting, it is easier in the following sense that what you do, you test whether there exists an undirected cycle of length up to say 2k plus 1. If you have, then you have found. It means the shortest cycle in the graph which has length at least k is actually strictly greater than or equal to 2k plus 1. Now you randomly, like not randomly, arbitrarily contract an edge. Look at that cycle. You have not made a no instance to an yes instance, right? But what would have happened that you had a very, very big cycle, you have just contracted some edge. But since this shortest cycle also had length 2k plus 1, even at least one of the side will have length greater or equal to k, right? So you can apply this m times and be done with it. But you cannot do this in undirected setting because what could happen is that, look, I may not even have a cycle, but once I contract this, I got a cycle. So I can make a yes instance to a no instance. Sorry, no instance to yes instance by contracting, right? So this idea is not going to work, but that at least tells you, I mean, to what happens to the structure of directed graphs or to the shortest length cycle when you do not have cycles of length up to some factor. Okay. So the trivial idea is to try is the following. So first thing which I will try today, check if there exists a directed cycle of length L between 2k plus 1, and this I can do using color coding, anything. I just want to check in my directed graph, is there a directed cycle of length between k and 2k plus 1? If it is answer is yes, you return yes, otherwise answer is no. And then I want to check a cycle which is greater than equal to k, in fact whose length is greater than equal to 2k, strictly greater than equal to 2k plus 2. This is what I would like to check, right? So we are in this case, we are assuming that the shortest length cycle whose length is more than k is actually much larger. That's all that I, okay. Okay, so let C be the shortest cycle whose length is more than k. Okay, this is the shortest cycle whose length is more than k. Okay, so let's look at this cycle. Say, what is the cardinality of C? Because we are in this case, in fact, this is 2k plus 2. Okay, excellent. Now pick any vertex u and say u1 and go up to uk, anywhere, and list W2k. Okay? Our claim is, look at this U1 UK, right? Can there be a path from U1 to UK? Can there be a path from U1 to UK which intersects this portion and which is disjoint from WK plus 1 to W2K? Vertex. If it will intersect in vertex, it will edge, it will also intersect in vertex, right? Okay. So now let's look at the shortest path between U1 to UK. Look at the shortest path between U1 to UK in your graph. My claim is that cannot touch this portion. Why? Because if it touches this portion, then what can I do? I can just go from here to here and come back here, and this is still a cycle whose length is more than k, right? But it is shorter than cardinality of C. But I have assumed the C the shortest cycle whose length is more than k. Okay. So what do we know? From U1 to UK, if you are looking for paths of length at most k, these guys are not touching these portions. That's all that I know.
So what happens if they can touch between WK plus 1 to 2k?
Which one?
So this path, the shortest path, can it touch even WK plus 1 to 2k?
Can.
That it cannot touch anything outside.
Anything else in the cycle. It cannot touch anything else in the cycle.
No, he is claiming that it can not touch anything between 2k to V1.
This one.
Yeah. But can it touch something something between wk plus 1 to wk.
Shortest path from V1 to Vk?
Yeah.
Yes, because you can have a cycle whose length is shorter than k
So it can.
through that. Right? So
It
you
can.
say V1 and then you go to some W1 and come back to Vk.
Yeah. So it can.
Then that there is no real contradiction.
There's no real contradiction. All I'm saying that it doesn't touch is this portion.
Yeah,
That's all. Look at any path of length at most k. Okay, it cannot touch here.
But you have assumed that your shortest cycle is greater than 2k plus 1, right? So
Yes.
you touch between W1 to
No, you're not assuming shortest cycle is at least k. Shortest cycle whose length
Greater
is
than
greater
than k.
Among cycles whose length is greater than k.
Whose length is at least k. Right? That's it. So all that is required for me is this is all that is required. Okay. So now let's look at all the paths of length k. It can intersect W-wise. I'm not telling you that it will not intersect W-wise. Okay? It can intersect. Okay? But look at what I call path between U1 to UK. Okay? Path between U1, UK of length k. All paths. This is my all paths. Okay? Notice one thing. U1 to UK doesn't intersect WK plus 1 to W2K, right? So, if I think of WK plus 1 WK2K as Y, if I as a Y, then I have X in me who is disjoint than Y. Do you agree? And none of these paths intersect anyway here. Like none of these paths intersect. I told you that none of these paths can intersect here. They could intersect here, that's perfectly fine. But I am saying in my family, there is a path which is this. So now what I would like to compute is, imagine I computed k representative. I am computing k representative of this. So I got P prime U1 UK k. What is a k representative means? If you give me any path of length k, look, and all these are paths from U1 to UK. If you give me any set which is disjoint from here, then I will give you another set here which is disjoint from here. That's all. But everything here is a path of length k. Right? So what my algorithm will do now, enumerate each path here, say P. So I have U1 to some, but all these paths are from U1 to UK. I don't know what is inside. And I delete this and I see, okay, in D minus, say X, check if there is a path from UK to U1. And that's it. So if I check if there is a path from UK to U1 which avoids X, then I have found a cycle of length at least k, right? Right? And I'm guaranteed that this rep set which I have computed the k representative of these objects had such a path, because if you give me U1 to UK, right? So think of this as your X and this is your Y. Then here I have an X such that W and WK, so you give me your favorite Y for which X intersection Y is phi. So my rep set contains some X prime which is a path from U1 to UK, okay, where this, which is disjoint from Y, okay. Then, and what more do you know, because of, it does not intersect any of these things, right? So it doesn't intersect any of these things, then I can replace something with here, and then if I look for a path, and it definitely doesn't intersect WK plus 1 to W2K, because that is what my Y is. So it doesn't intersect this now. It doesn't intersect any of these things now. So there is a path from UK to UK plus 1 which avoids whatever I have. So if I delete this guy and ask for a path UK U1 in my graph D minus X, I will find such a path.
Where are you using the fact that it doesn't intersect anything?
To ensure there is a path from UK to U1. Otherwise, how can I ensure?
So that there is a path from UK to
U1.
avoiding this entire cycle? No.
Look, it definitely avoids this. But maybe it picked up some vertex inside here, right? Then I know, may not have paths from UK to U1 because maybe this path is broken. Maybe it was a unique path. Imagine that this is a unique cycle. So by the property of shortest cycle, these paths have a property that these guys avoids these things. That's one. And by the property of rep set, I have made sure they are disjoint from WK. So this is finite object. So I can make anything disjoint from finite object. But this is a very long thing, right? So which I cannot make. So just by choosing cycle which C is shortest, I have made sure that, look, all of you by definition are disjoint from here. Like none of these guys intersect any of these guys. But because of the property of rep sets, I have made sure that you are also disjoint here. So that's it. Okay? Okay. So this is, and how will you compute this? Just the way I computed rep set for path. You start from U1, then U2, add everything else, refine it, go further. So this is exactly the same rep set computation here, right? But like now I have a k size, so basically your p plus q is actually 2k. Like my x could be as bad as this, and my y is up to k. So this is like going to be, this is, for example, this will be like 2k choose k, right? Because this is my p and this is my q, right? So when I do 1, 2k minus 1 rep set, 2, 2k minus 2 rep sets, here I'm done. Okay, I've got my object, which is disjoint from all this, and I compute. Any question? So this is from where this lemma comes, and there's an amazing property of this path. Is actually, if you do some red-blue coloring, then this is the shortest path between U1 to UK is actually exactly equal to k. You can show that, but that requires a. I will not go there. This is where, but this is where where we got the rep set algorithm. But now we needed to come up with a rep set computation, which is C power k, which is not p to the power k. Otherwise, that will give you k power k simple algorithm. Then we came up with this universal set construction to get this. Okay, but this was a starting point. So here I am starting at U1. I will make sure that I end at UK. Because what I was computing, if you notice, for every UK, this to this into this. What was you computing? You fix this, right? All the paths which start from here and ends at this and has size this. So my U1 is a fixed point, and I will compute it for everything. In particular, I will compute it for UK. Okay. Okay. So just to give you a feel. So this is another application of rep sets. Basically, it tells you that, I mean, it's very amazing. It's like it says you that you just look at this prefixage of paths, right? You delete them and then you check, and that's good enough. So it's very, in that sense, it's quite counterintuitive, at least to me. Okay. So up until now, I have never used the word matroids. I always work with set systems. But now, I will use set system, and the matroid which I will like to use and which we might see lots of application is called gamoids, which I'm not sure if was introduced to you yesterday. Okay. So let me first do a simpler version of gamma L. Okay, I will call it disjoint path matroid. So this is disjoint path matroid. So given a digraph D, and a source vertex, okay, my universe is H set of D. Okay? No. Universe is vertex set of D. And what is my family? X subset of VD if there exist mod X edge disjoint paths from S to X. Then this set I will call independent sets. So we have to prove three property. One, hereditary property. If X is element of F, then X prime is element of F, where X prime is subset of F. I mean, if you have a X disjoint path, then look at a subset, you just take those as disjoint paths. So it's hereditary for sure. But why does it satisfy exchange property? This is hereditary. But why does it satisfy exchange property? Okay, so what we have to show, if there exists X, comma Y in F, right, then there exists X in X minus Y such that Y union X is in F. Agreed? This is my goal. If I want to show that this forms a matroid, I have to show this exchange system. Which means if you give me two sets X and Y, where one has currently larger, then I can find an element from here which I can add. Did you do this for transversal matroid yesterday? Exchange property for transversal matroid? Okay. Hint, max flow min cut. It's not as hard as it looks to. It is actually easy. Max flow. Anybody sees an answer to this? Maybe it's a bit non-trivial, but I don't know. So here is my S. Okay. I look at X union Y. Here is my X union Y. Okay. I add a sink, which is T, like which is not present in my graph, and I add a directed edge from here. This is what I do. Okay. Every arc or every edge has capacity 1. What do you know? You know that S to T, there is a flow of value at least mod x, at least mod x from S to T. Do you agree to this? Because if x is inside I have that many arc disjoint paths. So if I put one unit of flow along those guys, then there's a flow from S to T of at least mod x units. It could be more, but definitely it is this much. Agreed? Okay. Okay, fine. there are also y arc disjoint paths. Okay, so there is also say py which is arc disjoint paths from S to Y. Do you agree? By definition of F. Okay. So I have S here. Suppose this 3. Okay. Consider the current flow where I have put 1, 1, 2 only on these guys, and look at the T here. 1. Okay. So consider this particular flow, current flow. What is the, how many unit of flow it is? Mod y unit, and rest is 0. Okay. Now if I do Ford-Fulkerson algorithm, I want to augment this network. What will you do? You will compute its residual network and you will find a path from S to T. Am I right? Okay. Notice one thing, look at the vertices of, these are my vertices of Y. What will you add from T? 1 unit of flow. Do you agree? In the residual network. Right? I have 1 unit of flow moving in this direction, then what will, so other direction has 0 and the flow is -1, so minus. So this is exactly what you will get, right? And S. Clearly, I know that there is a flow in this network of size mod y more than mod x, right? And now I want to compute an augmenting path. I like in this residual network, find a path from S to T. Find a path from S to T. Clearly that path from S to T is going to use something which is not in Y but somewhere else and then go to 2, because all they are just in arcs. You cannot go to T from here. Okay. So now if you look at the next augmenting path, like if you increase your flow along this direction, what have you got? You have got a flow from S to T which not only takes this, but it also adds one extra arc disjoint path by Menger's theorem, which passes through some vertex in x minus y. Sorry, what did I write here? Yeah. This is x, right? Oh, that was correct. Y. Yeah, so there exists.
I think it's only
Here there is a mistake. Okay. No, here also is correct.
only below. Now
This is the wrong thing, no?
x greater than.
Okay. So the current flow is y, and then I would have picked up some vertex x in x because those are the only guy who goes to T, right? So then I have got in this new flow, I have got a set of edge disjoint paths from S to T, which collects all the vertices of this and also adds one extra vertex from x minus y, and that's your proof. So this is your exchange argument. Okay. So it also follows from Ford-Fulkerson, right? So you have to be you have to build a network and start with an appropriate flow, not any flow, a flow which saturates your x, and then because of the arcs you have given, you can never go out of them. So but you know that in this network you have a higher flow, so that flow will only pass through the remaining guys because those are the only people who can come to T, and you can augment along those lines. Now you have everything, because now if you draw the flow, every vertex of x, every vertex of y would have been saturated, and you would have at least saturated one more vertex of x, and then you have shown the exchange property. Okay. Okay. So this is called disjoint path method. Okay. And now once I have given you this proof, you can come up with any, if I told you vertex disjoint, you can convert it to arc disjoint by subdividing arc and this, like the normal tricks which we do from arc to go to vertex to arc, and you can get all these kind of things. So what is gamoid? So this is not gamoid, by the way. Okay. So the gamoid is like something of this nature. So gamoid is the following. Input is D, S and T. Okay. Input is D and C. Okay. And your family is your universe is T, and the family is X subset of T. X is reachable by mod X is reachable by S with mod X vertex disjoint paths. Okay. So what it means that I have S here and I have T here. Okay. So I'm going to call this, if I can find some set of vertices here, so there is a vertex disjoint path from here to here. Then this set is called is part of my independent set. Okay. Okay. So this is exactly what gamoid is. Okay. And next is something called a strict gamoid. Where T is vertex set of T. So like I do not restrict myself to some subset of T, but I could have any subset which is reachable with some. So what will be the rank of this family? It is upper bounded by cardinality of S. You cannot have more than that vertex disjoint path. Okay, and you can again prove this is a matroid using all these tricks. Right? Like you don't need to do. Okay, so I have told you about what gamoids are and everything. Okay, so now what I'm going to do now is, so we will use this object quite a lot when we will get to kernelization of lots of objects using depth sets. Okay, so these are the objects which will come flying on our face all the time when we will do kernelization for problems like vertex cover matching or cycle transversal and almost two set and all this kind of thing. Okay, so this is what I wanted to tell you. But now let's generalize our concept of representative sets from set family to matroids. Okay, so let me use here. Okay, so you have a universe, like you have matroid M, so which is over universe and family of independent sets. Okay, now suppose H is p-sized independent sets of F, right? So H is some family of p-sized, but they are an independent set in this matroid. Okay? Okay. Now I'm going to call H prime subset of this Q representative of H if the following two properties are hold. Okay? For all y mod y equal to q, okay, there exists x in H prime so that x union y is independent, okay, for all y mod y equal to q, let's such that A x intersection y is empty and B x union y is independent. Okay, then there exists x prime in H prime. Huh?
Exists X belongs to H, not H.
Correct. Okay, there exists x prime in H prime such that A x prime intersection y is phi and B, okay, x prime in y is independent. So I will remove the property A by saying the following thing. I will say x union y is independent set of size p plus q. Right? If I say this, then I don't have to say x intersection y is phi. That is like encapsulated in this. Okay, so I will remove this. Is independent set of size p plus q. Okay. Now, yesterday, Fahad also would have taught you what is called linear matroids. Okay. Did he teach you what linear matroids? So basically, an M u comma f is called linear matroid if the following happens. Okay, I can come up with a matrix. I can come up with a matrix of size some. Actually, you can come up with rank of m times cardinality of u. You can come up with this much with the following property. Okay, or let's say T cross U, such that what is the property? For there is a bijection between U and columns of say matrix what of columns of A. Okay. Okay. So this is what it is. And now what is the property? Okay. X is in F if and only if X is in F if and only if X is linearly independent in A. Right? So if you look at the corresponding columns in A and you look at the normal linear independence, then they are linearly independent. And that is why they are called independent sets actually. So now this is why now if I do Gaussian elimination, I don't change the rank of a matrix, right? So I can make T as nothing but rank of those. Okay. Now, so there could be a matroid where given a matrix M, okay, I can think of my universe as columns of M and my family X subset of say column of M, X is linearly independent. Is this a matroid? If some set is linearly independent, then of course all its subsets are linearly independent. But if I give you X and Y, mod X is less than mod Y, okay? These are linearly independent. I have to add something. So let's look at, suppose these are my Y minus X columns. Can I add this here? I want to extend this, right? Otherwise, how will I prove exchange property? What happens if this is written as a linearly independent, like as a linear dependent of all this? If this is linear dependence on this is linear dependent on this. What is the meaning of this then? Y is? Because then Y is not linearly dependent, right? Because x belongs to y. So at least I can add one thing here such that this guy and this will be linearly independent. Okay. So that is why all the terminology of matroid comes from linearly independent, basis, rank and everything. And look at any matrix. Look at what is basis is a max like largest size independent set. So since largest size independent set, all bases has same size, right? So this is why if you look at exchange property, it implies to you all the largest size independent set has the same size, right? So all this terminology comes from here. Now notice this f could be really huge, right? But this matrix could work as a very good oracle for the following object. If I wanted to check, if I give you, universe is small, I give you a set, I want to know whether this belongs to independent set or not, right? I cannot explicitly store f, it could be very big. But if I have a small matrix, I can just go and check whether this is linearly independent or not, right? So this is a very good property of this, right? So any matroid which can be written as this is called linear matroid. There are non-linear matroids too, right? Not all matroids are linear, but most of the matroids which we would be interested in are linear. So for example, Fahad would have told you how to write the representation for graphic matroid yesterday, how to write a representation for uniform matroid, how to come up with a representation of transversal matroid by Schwarzschild, right? And since, take it from me, gamoids are a dual of transversal matroid, it requires proof, they are also representable. So all these objects are representable, okay? But if you look at transversal matroid, there was a randomized algorithm to construct this representation for transversal matroid, because what we did, we randomly substituted this value and used PIT to say that, hey, this is a representation with a good probability. And since I am taking a dual of a random matrix, it is also a random matrix. So gamoid also has randomized polynomial time algorithm to come up with its representation. So that much about representation, but that is not what I wanted to tell you. So this is a notion of representative sets for the matroid. Okay, I would like to, okay. So here is my linear matroid. So I have M, U, F, and let's use AM, okay, to represent this linear representation. Just as a AM is linear representation. Okay, okay, excellent. Now I have been given an H p-sized independent sets of M. Okay, and goal, compute okay, this is my goal. First of all, not clear is what? You could relate it to Boloba's lemma and do everything and did something. What should I do here? Right? It's not, I cannot apply any more Boloba's lemma because there is an independent set in a matroid, which means that I am talking about independence in this matrix, and that all this there was disjoint paths. So, okay, what do you think? What is an answer? Do you think such objects exist? And if it is, what should be the right answer? and there is no combinatorial proof for this. So only proof we know is using algebra, algebraic geometry. Okay, so let's prove this. That's the goal. Okay, but I'm using its linear matroid. For non-linear matroid, this may not be true. Okay, I'm going to make one assumption at this point of time. Okay, and I will remove that assumption at the end of this. So what is my assumption? Is AM is P plus Q times n matrix. Okay, but rank of a matroid could be much higher. Look, here I am writing rank into this. Rank of a matroid could be much higher, right? So this may not be true at all that A has to have a P plus Q cross n. But let's do the proof even for this case, and then we will get to how to get to this starting from AM, right? If you give me normal, how can I plug in this? Okay, we will leave the thought for some time. Okay, how many of you know? So if I give you do you know how to find determinant of this matrix? So how? What's your algorithm?
Take any row you want to expand.
So let's say I can also expand along column, no? So let's expand along first column.
So take the first element.
First element.
Sign will be the sum of whatever position it is. Sign of that.
So here it is minus 1 to the power
1 plus 1.
1 plus 1. Let's keep sign times
Now the cofactors will be 7 into 2.
which is determinant of. Is that correct?
Yeah.
Okay, excellent. Next.
Again, 5 with sign. Sign would be 2 plus minus 1.
So we will add this. So I will add plus. Okay. So plus determinant of. Huh?
Multiplied with 5.
What?
You didn't add like with 5. Multiply the determinant by 5.
Oh, fine. Sorry, forgot. 5 times
2 into 2.
2 into
2, 3, 2, 2.
2, 3, 4, 2. Excellent. Very good. Next. 3 plus 1, right? Times 6. Perfect. Okay. Good. So let's write down. What is the sign of, what is this number? I want to write times 1. I want to write minus 1 to the power 2 plus 1 times 5. Minus 1 to the power 3 plus 1 times 6. Okay, let's call it vector A, let's call it vector B. So what is A dot B? Huh? What is A dot B? What is A dot B? This into this plus this into this plus this into this. This is exactly what you wrote as a determinant, no? So if I take the dot product of this, Does it make sense, no? So I can think of maybe determinant, it's a dot product of two vectors. Okay. I did not do any magic. Okay. You try. I mean, you try. If you wanted to try expanding along this, corresponding to that, I will get this. So I will put it here. Corresponding to this, I will get this. I will add it here. Okay. So this is your school maths. I want to just change it a bit. So I want to say this is determinant of this matrix called 1. I want to write this is nothing but determinant of matrix called 5, right. I want to write this 6 as determinant of this matrix called 6. So determinant of 6 is 6 itself, right. So I have not changed anything. So basically here is also some determinant, here is also some determinant. For now let's forget about this sign. For now let's just forget about this sign. We'll get to the signs later. Okay. Okay. Let's do some funky maths. 1, 2, 3, 5, 7, 1, 6, 4, 2. I want to expand along these two columns. Have you seen this? I want to expand along these two columns. Or should I make a slightly bigger matrix? Then I will get myself confused, so I'm not trying to do. Look, who has stopped us from expanding along one column and one row? I actually want to expand along two rows, two columns. Okay. But why? So, but how should I go about expanding? What is your definition? What is the meaning of this? So, what I associate a following meaning to expanding. I said, okay, fine. If you are going to talk two row, fix. This is the two rows you fixed. What did you go? Then you went along column, rows. I also want to go along rows. But imagine yourself, I have fixed 1, 2. Fine. Now, what do I do? What matrix am I getting? Huh? 2. Or should I take 1, 2? Then there is no meaning of this determinant. But if I had taken, fine. Let's write down 5, 7. 1, 2, 5, 7. Then it makes sense. No? Then this is like cross all the rows. This is what, and then whatever is left. Okay. Okay. So let's do this. But then I should go over all possible two-side subsets here. All sides two-side subset here. Excellent. So let's go through all possible two-side subset here. Okay. Here. Okay. So minus 1, we'll write down what something to do. So what is this? So this is determinant of 1, 2, 5, 7 times determinant of 2. Some sign, fix that, we'll fix that. Now next is 1, 2, 6, 4. Right? I first fix 1, 2 and go through all subsets. So plus minus 1 something, and determinant will be 1, 2, 6, 4 times determinant of what? 1 plus minus 1 something. What is left? This is only two subset left. 5, 7, 6, 4 times determinant of 3. Okay. What were you writing here? Minus 1 to the power what? minus 1 to the power, what were you writing here? Index of, so what were you doing here? Row plus column. Fine, here I will do summation of rows plus summation of columns. This is what I want to do. Okay, so this is my new generalized definition. Okay, let's see if with this definition, if these two guys are same at all. Right? And I leave the proof to you that they're same. Okay, so this is what? Minus summation of all the rows involved in this plus summation of columns involved in this. This is my, the what do you call, sign will be. Sign will be. Okay, at least let's compute that they are same. Can someone compute this? Okay, so this I can compute. 7 into 1, 7, minus 5, 2, right? Correct, no? So minus 3. So minus 3, and what is minus 1? What rows are, look, I am fixing column. So I actually would have taken out minus 1 columns outside for all this because they are going to be same for everybody. It's the rows which are going to change. So what is minus 1 to the power columns? First and second column. So 1 plus 2 is 3, so this is minus 1. And now first and second row, this is also 3, so minus 1, so this is going to be nothing here. So minus 3 times 2 plus, this is minus 1 times first into third row, right? So 3 plus 1, so that is nothing, so this is going to be minus 1 times what? 4 into minus 6, so minus 2, okay, and do something. You will check that they are same actually, okay. So there is no hard and fast rule about this, okay. And I can also think of this as the vectors again. How? Look at this two-side subsets, okay, two-side subsets. If I go over each two-side subset, I get a determinant object. And then take the corresponding guy which you get as a what you call cofactor. Just write it down there, right? Then the determinant is nothing but multiplication, like dot product of these guys with their signs, and that's it. Okay. So this is called generalized Laplacian formula. Okay. So what does it tells you? Okay. So there is no hard and fast rule how you are going to expand it. You can expand it along any subsets of columns or subset of rows. Okay, so let me write down exactly what it is, otherwise maybe I might make a mistake, which I don't want to. Oh no, this is not what I want. Okay, so suppose here is your A and here is your n cross n matrix. Okay, and suppose you have chosen some S subset of columns to expand along. Then the determinant of A will be summation over, okay, J subset of rows of A, J is equal to cardinality of S, right? And I will tell you M J S is a matrix which you write down. Like, so MJS will be, you fix these rows and these columns, right? So this is what it will be. Matrix with rows restricted to J and columns restricted to S, okay? So here I will write, I go over determinant of MJS times determinant of, now S is fixed and J is fixed. So there is a minor which forgets this and forgets this, which is nothing but determinant of M. So what rows now we have? It is row space, row of A minus J, comma, columns of A minus J. That's it. Minus 1 to the power summation I in, so I I in S plus summation j in j. Okay, so or let's call it. Okay, so here is sign. Sign is nothing but minus 1 to the power summation I plus summation j, where I is what? I is in your j, choose anything, it doesn't matter. S and j is in your j. That's it. So this is your Laplacian, right? Excellent. Huh? Column?
Second term is column of A minus J.
Like look at, sorry, minus S, sorry, delete all. So this is your generalized Laplacian formula, and if you know how to write, like how to prove determinant using this permutation, then this is like, this is exactly the same thing, it shouldn't take you much time, okay? Notice one thing, what we are going to use the fact. What is n choose I? Is also n choose n minus I, right? So when you choose I rows, you are also choosing n minus I rows for the other people, right? But they are same, right? So that is why when I write this as a dot product of vectors, this is exactly matches, because on the top you are finding a determinant of I, but bottom you are writing n minus I. So how many such terms are there? N choose n. So I am just putting them together like parallel and taking the dot product. Okay, so this is what I want to do. Okay, is this idea clear? Okay, so now let's go back to our matrix. So this is, we took a digression and talked about something about Laplacian. Okay, so what I would like to do, so think of this way, right? So now here is my matrix AM, right? And now my H is given, say S1, S2, SL is given. But what is this SI? SI is some set of independent columns, right? This is some set of independent columns. And what is my goal? My future is also some set of independent columns, together they are independent. Because it has a size P and Q, and both have size P plus Q, so it will be, together they have to be independent. And for now, I have assumed that it is P plus Q cross N matrix. So what is the determinant of this columns and this column will be equal to non-zero. Look at the matrix corresponding to S1 and his future, which is going to come, say Q1. So what is the determinant of matrix? Rows remains rows of AM, and my columns is S1 union Q1, right? You said that this is linearly independent. It has a dimension P plus Q times P plus Q, because this is a P size column, this is a Q size column. So this is equal to, not equal to 0. Only then these guys will be, they will be independent set in my matroid. So I want to use that property. Okay, good. Now, what I am trying to achieve all this? What is SI? SI is a subspace. So if I think of a matrix being, this is a matrix of some vector space to some vector space, then SI represents some subspace. Now subspace is very hard to see. I want to map a subspace where these objects are subspace to another vector space where each subspace corresponds to a vector. Okay? Okay. And this is exactly what is called exterior algebra. I am not going into those. But what and how will we achieve this? I am going to give an algorithm to achieve this. So it's like I am preparing myself. Look, if with respect to S1 Q1, I am going to have a determinant non-zero, let me try to keep myself expanded along S1 so that the future vector which comes in Q1 will take dot product with me and will be non-zero. Okay, so can I create a vector for S1? So how do I create a vector for S1? S1 I create a vector which is like sine, okay, sine, but basically you go over every, so here indexed by p sized subset of rows of AM. Okay, so this is what you're indexed with. Okay, and you write down the -1 to the power whatever, right? So rows, columns are fixed, so you add that times another -1 or to the plus whichever rows sums you are going to take. But this I can see, right? I am deciding which rows to pick, and determinant of this object. This is some number I can compute. So I can compute this vector and keep. So what is the length of this vector? The vector length is p plus q choose p, right? So if I have L objects, how many vectors do I create? I create, say, S1 vector, S2 vector, SL vector. L vectors I have created. And what is the dimension of these vectors? P plus q choose p. And what I am going to do, these are vectors. So I am going to compute a basis for this vector. Okay? Compute a basis for this vector. And this is easy to compute. You make a matrix, do Gaussian elimination. Okay? Compute a basis for the vector. Let's call them, I don't know what to call them. I already used hat. Okay? Q1 hat, Q2 hat, Q. Okay? What is an upper bound on T? It cannot be more than P plus Q choose P, no? Because think of this as a big row matrix, right? I put down or column matrix. What is the dimension of this matrix? If I put each of them here S1, SL, then this dimension of this matrix is L times P plus Q choose P, right? Write down. So if the matrix dimension itself is P plus Q choose P, you cannot have a basis more than this. So all I need to show that this will do a rep set's job, then I am done. Then I have not only given you proof that P plus Q suffices, I have also told you how to compute those rep sets. So what I mean by Q1, Q2, they correspond to some vectors here, right? Take the corresponding sets there, right? Now I need to show to you why this is a rep set. Okay, so let me try to prove to you that why this is a rep set, and then we will end. Then I will tell you why, how do we achieve this, and then I will build with the stop for today. Okay, I can drop this. So what is my H prime? Take S such that there exists I and Qi hat is in, say this set Q. Okay, so this is what my representative sets are. Now I have to prove this is a representative sets, right? How do I know otherwise? Right? I know that the H prime has size P plus Q choose P. Okay, we'll come back to the running time of this algorithm a little bit later, but let's first prove this is a rep set. Okay, fine. So I have some S in H, okay, and you have some Q. This is such that what is the property? S union Q is a P plus Q independent sets. Okay, what is the property of this? Then if I look at the determinant of this matrix restricted to S union Q is not equal to 0. Agreed? Okay. If S is in H prime, nothing to prove. We have our rep set. So S is not in, so S is not in H prime. Okay, fine. Okay, great. So look at the corresponding vector F hat. This can be written as summation, because this is basis, right? So I can write F hat as linear combination of these things, right? So let's write down. So S hat is some lambda I times Qt hat. Agreed? Sorry, Qi hat, where I going from 1 to t. Can all lambda I be equal to 0? No. There exists some lambda I which is not equal to 0. Okay? You can actually show that all the lambda i's for which this is not equal to 0 can replace S hat. Okay? Why? Let's try to. Okay, so I think of my determinant, look, as S hat, right? And look at your Q, right? You make a corresponding Q vector correspond to Q. Look at the determinant of S union Q. I write down my S hat vector, and with respect to Q, I write down Q vector, right? Determinant of this, determinant of this, determinant of this. What is the property of this? S hat dot Q hat is not equal to 0. Fine. So I want to multiply this with Q hat both sides. Okay, fine. S hat dot Q hat is equal to I not equal to 1 to t lambda I Q hat times, sorry, 2 times Q hat, everything. This is not equal to 0, right? If this is not equal to 0, then this side also cannot be equal to 0. So there is some non-zero term. Just pick that non-zero term. So look at this Q hat, which is non-zero. What is the meaning of the Q hat dot Q? So Qi hat is some set, and this, if you look at their determinant, that is non-zero. But what is the dimension of that? P plus Q. So this and this will be packed together, and that's it. Right? So I look at S hat dot Q hat. This is not equal to 0, and so this is, since this is left hand is not equal to 0, right hand cannot be, every summand of right hand cannot be equal to 0. So look at the non-zero summand. So what is the meaning of non-zero summand? Look, lambda I is non-zero, because if lambda I is a 0, forget it. So I only take here which is lambda I is not equal to 0, because and this is also non-zero. This is not 0, this is also not equal to 0. Let's look at those. What is the property of right? So sum Qi hat dot Q is not equal to 0. But what is Qi hat? Some set of columns. What is Q? Some set of columns, and the determinant of this P plus Q times P plus Q matrix is not equal to 0. It means this which I have stored here times into this are linearly independent, because why? My matrix has dimension P plus Q. Rank is P plus Q, right? So this is how I can obtain my rep sets. And what is the running time of this algorithm? Well, let's look at this. What did I do? I can compute all these vectors in running time. L, if I have L vectors, L times, right? I have to compute, make this big vector, right? So P plus Q, choose P, because that many entries, and for each, what are you doing? You're just computing some P times P determinant, right? Which is can be done in P to the power omega time. Okay, great. So in this much time, I can compute this matrix, right? And how much time do I need to compute the linear independent? All I need to do is I can do this in matrix multiplication time. So if I can do this in matrix multiplication time, then basically I can do this in P plus Q, choose P to the power omega, where omega is a best matrix multiplication exponent, and I'm done. But why on earth A was P plus Q times M? No reason. So let's fix that.
There you choose the Q that is some q such that s dot q is not equal to 0.
Where?
The q that you have chosen.
I started with S, you have some matrix Q.
Yeah, no, there.
Where? Here? Then what is the property of if you have chosen S and Q? So with respect to S, you make a vector S hat. With respect to Q, you make a vector Q hat. And what the like think of this as a matrix, S union Q matrix, right? Q. It's a P plus Q times P plus Q matrix, and I'm expanding along S. So I wrote down this vector, then I write down the determinant. S hat dot Q hat is not equal to 0 because the determinant is not equal to 0, and this object is only computing determinant. And then, okay. So let's get rid of this constraint about okay. So this will work when my input linear representation AM has dimension P plus Q times whatever. Wasn't this wrong? This was correct, but A was like this, fine. Dimension P plus Q times N or whatever, right? But all I can guarantee that given a matroid M, I can give you AM, which is, what is his dimension? Its dimension is rank of M times N. Okay, so there is something called truncation of matrices. Okay, so now let me define this operation called truncation of matroids. Or matrices, doesn't matter. Okay, so you are given M, universe, and F. So what is a K truncation matroid? And what is FK? Keep all independent sets of size at most K. Trivially, it's a matroid. This is called K truncation matroid. Right? I only keep independent sets of size up to K. Right? So given AM is some representation of M. All I need to do is compute truncation of MP plus Q, no? Because all independent sets of size P plus Q are preserved here. And I'm only interested in those independent sets. I'm not interested in bigger independent sets. So rather than working with AM, I could work with MP plus Q. And there are lots. So if AM is representable matrices, then you can compute its representation like by left multiplying with some random matrices. But there is also a deterministic way of getting this K truncation in polynomial time. Okay, so this is how we get over this. So otherwise, what we would have done, given a matrix, I first truncate, right? On the truncated matrix, I compute my Repset algorithm. Okay, so that's way you get over this condition of artificial condition of P plus Q times N, right? That you, and what is the truncation? It only preserves independent sets of size at most K, right? So this is like K rank preservers. Okay, so given a matrix M and a number K, in polynomial time you can come up with another matrix M prime of dimension K times N, which has the property that X is independent in M if and only if X is independent in here, but since it is K, it's only K. Okay, so this is called truncation of matroids or matrices, whatever you want to call it. Okay, so what I have told you is that representative sets or families are not interesting objects for the universal matroid or for the set family. Notice, what is the property of this construction? It will also work for uniform matroid, which is nothing but whatever the set family what I was doing is nothing but an uniform matroid. So I have given you another construction. Here I don't have any blow up of K to the power log K or nothing. It will purely give you P plus Q choose P size Repset. But the running time is slightly more higher because there is a matrix multiplication exponent sitting there, right? But it outputs you a Repsets of the best possible size. when I say best possible size in terms of upper bound which we can achieve, though the running time of this construction is higher than before, right. But it not only works for the set family, it works for any linear matroid. Okay. So, be it graphical matroid, be it co-graphical matroid, be it gamoid, be it transversal matroid, anything we can compute this. In next lectures, I will show you one or two applications of this in kernelization. So, that will be the goal.